Okay, in this video we're going to differentiate some expressions where x and y are the wrong way round. This should remind you, in fact this is a case of inverse functions, okay? So the normal function would be y equals 9x squared. We've now got x equals 9y squared, but we still want to find dy by dx, okay? Well, looking at this expression, one approach would be to rearrange it, make y the subject, so it's the correct way round, and then differentiate normally. Okay, but I'm going to deal with the function in this rearranged inverse form because I can still differentiate what I see. If I differentiate 9y squared, then I'm going to get, well, y squared differentiates to 2y, 9y squared will differentiate to 18y. But then I need to think, what is this that I've found? Well, x and y are the wrong way round, so I haven't found dy by dx, I've found dx by dy. Right, how's that related to dy by dx? Well, the fraction has gone the other way up, okay? It's actually this relationship here. This is what you'd expect to happen with fractions. Technically, dy by dx and dx by dy aren't fractions, they're derivatives, okay? But when you turn it upside down, you're still doing a reciprocal. So if I want to turn this dy by dx, sorry, this dx by dy into a dy by dx, then I need to do the reciprocal. So the answer is 1 over 18y. Okay, and I think I'm allowed to stop. This is a slightly unusual answer for dy by dx because it's come out in terms of y, but that's because my original function was given with x as a subject of the equation. So I think I'm allowed to stop here. Okay, part B, now this is a very interesting one. Okay, for this one, okay, if x equals e to the y, what did the original function look like before it was rearranged? In other words, what does y equal in terms of x? Okay, well, in order to get y on its own here, I have to get rid of the e by linning. So I have to do the same to the other side, so y is log x, or ln x. So what's going on in part B, although the question doesn't say it, is we are differentiating y as log x, which you may already have seen a rule for, but this is the proof of that rule. Okay, which you may already have been shown in the class, but if you haven't, this is where it comes from. So if y equals log x, our first step would be to turn that into what this question asks for, which is x equals e to the y. All right, so differentiate what I see, so I can get dx by dy. Well, that's very easy. Differentiating e to the y, e to the power anything differentiates to e to the power of y. All right, and then I want dy by dx. So dy by dx, okay, how do I get from dx by dy to dy by dx? I just do the reciprocal. So it's 1 over e to the power of y, which I could turn into e to the power of minus y, but I can do something even more fun than that. I can say e to the power of y, I had in the original question, e to the power of y is x. Okay, so this is 1 over e to the power of y, but this is just x, so the answer is 1 over x. Oh look, we've just proved that if y equals log of x, then its derivative dy by dx is 1 over x. So we've actually just proved the basic rule for differentiating log x. And you could be asked to do that in the exam, okay? All right, but it's just an application of this method. You differentiate what you see, x in terms of y, and then you do the reciprocal. And then there might be, like there was here, a little bit of substitution back we can do. And that's what we're asked to do in the last two. In these two, we've got to give our answers in terms of x. So I've got to do that last step. Okay? So this again is going to prove another rule for differentiation. In this case, it's one of the ones in the formula book. Okay? We'll see that at the end. So if x is sine y, I want dy by dx, but the first thing I can work out is dx by dy. Just differentiate normally. So dx by dy differentiates sine y, I get cos y. But I want dy by dx, so going from this to this is the reciprocal, so it's 1 over cos y. Now you may think it would be sec of y, okay, maybe it would, but it's not very helpful actually. All right, what I've got to do is express this in terms of x, and remember x is sine y. So if you, in a sense, I know what sine y is, it's just called x, but I want to know what cos y is. So what's the relationship between sine y and cos y? Well, these are always related by sine squared y plus cos squared y equals 1. So cos squared y is always 1 minus sine squared y, using the identities we've studied. So cos y is always the square root of 1 minus sine squared y. So that enables me to write this. It looks uglier, but this shows that it's correct. I can write this as the square root of 1 minus sine squared y. Okay, but what's sine squared y? Well, x is sine y, so this is the square root of 1 minus x squared on the bottom. 1 over the square root of 1 minus x squared is dy by dx. So I've just differentiated this function, but this is just a strange way of writing the original function, which was y equals, if I make y the subject of the formula, y is inverse sine of x. Okay. All right. Now you may be thinking, when I did this square root, that I should have had a plus or minus in front of that square root. If you were thinking that, then good for you. But in fact, the inverse sine of x, okay, if you remember the values of the angle that we use for the inverse sine graph looks like this, okay, and the angles here are the units on the y-axis, and it only goes from minus pi by 2 to pi by 2. Okay, so those are the angles that are used in the inverse sine function. All right, and if I think about my cost graph, this is an ordinary cost graph, not an inverse one. Between minus pi by 2 and pi by 2, the cost graph does that, and lo and behold, it's always positive. So that's why I was actually correct in not putting plus or minus here. But this is a case, and this sometimes happens, particularly in Core 4, where sometimes thinking about all the detail, okay, makes your life more complicated. If you have to do this, then I hereby give you permission to just not to worry too much about this particular plus or minus. Nearly always you do have to worry a lot. Anyhow, we finished that one. The last one's going to be much easier now. So x equals log of 5y, okay, and I've got to find dy by dx in terms of x. Now, because log is kind of an inverse function anyway, this one would be very nice to do, just by rearranging the original equation to make y the subject. But we're not going to do that. We're going to stick with the spirit of it. We're going to get dx by dy first. So how do I differentiate log of 5y? Well, I've taught you to differentiate logs. Logs differentiate to a fraction, okay? On the bottom of the fraction, we get the thing that was originally inside the log, which is 5y. And on the top, we get the derivative of that. Differentiate 5y, we get 5. And 5 over 5y cancels down to 1 over y. Lovely. Okay. But I've got to give the answer in terms of x. So I've got 1 over y. I've got to express it in terms of x. So it turns out that I'm going to have to make y the subject of this anyway. So if I make y the subject of this, the first thing I've got to do is find out what 5y is. Well, I've made the log go away. How do I do that? I have to e it. So therefore 5y is e to the x, so therefore y equals 1/5 of e to the x. So therefore 1 over y, so dy by dx I already knew was 1 over y. Hang on, let's be careful here. This wasn't dy by dx, it was dx by dy. I've written dy by dy. My pen's kind of half remembering what I should have done. Right, so dx by dy is this 1 over y. Okay, well actually let's go to dy by dx from that. So dy by dx is the reciprocal of 1 over y. The reciprocal of 1 over y is easy, it's just y. Oh, so it equals 1/5 of e to the x. Okay, so what I've done here is I've just done a very long process when I could have done a quick one. I had to make y the subject anyway, and if I look at what I've made the subject, y equals 1/5 e to the x, well dy by dx is 1/5 e to the x, because when you differentiate e to the x, you get e to the x. So in this particular occasion, using this dx by dy method turned out to be quite a long way round, but it gave the right answer, so we're happy.